Alright, so in this question, we're going to go and find the steady state error for 3 different inputs, and we're going to double check that our system is stable as a first step. Otherwise, the steady state equations don't make any sense at all because you have the unstable system. So let's look at stability. So for this, we're going to need to find the closed loop transfer function, or the overall transfer function of this system. So if we start with the open one, okay, that's going to be when we just consider the top line of our system and don't consider the feedback loop. So if we're just looking at the forward transfer function, this is going to be what our open one is. Okay, and now what we need to do is find the closed loop transfer function, and for that we need to know what is in our feedback loop, calling that transfer function h, and since we have unity feedback, where it's just directly whatever is at the output is fed back, h is equal to 1. So we can go find our closed loop transfer function, or our overall transfer function it's sometimes called, the general equation for the negative feedback. Looks like this, and if you substitute these into the equation, because we have unity feedback, what we end up finding is the simplification of this equation is the open loop transfer function with the addition of whatever's on the top line also appearing on the bottom line as well. So I'm going to shortcut it and just write out what it will simplify to. Go back and look at some of my earlier videos if you want to see the actual simplification process. Alright, so that's what my closed loop transfer function ends up being, and if I want to perform a Ruth table analysis on this, I'm going to need to know what each of the coefficients in front of the s's are, which means I need to expand out the bottom line. So if you go to that effort, we end up with s cubed, 27s squared, 168s, and 18. Alright, so let's set up our Ruth table. We need to look at the highest power of s, which is going to be s to the 3, and set up our rows based on that. Give us some columns. So the coefficient in front of s to the 3 is a 1, s to the 2 is 27, the constant s is 168, and this one is 18. Everything else, remember, as you keep going, can be filled in with a 0 if you need it. So we need to look at whether that we've got any sign changes in the first column. At the moment we have 2 positive values, which is promising. So we just need to double check that these 2 are also positive, and that would mean that we have a stable system. So I'll just call this A, and we'll go and work it out at the side. So it's going to be the negative of the determinant 127, 168, 18. And we need to divide by the pivot element, which is going to be 27. And this works out to be 167.33. Alright, so again this is positive, so we're still on track to have a stable system. We just need to figure out this last one. This box here we can get from the determinant of 127, 0, 0. Since these are both zeros, the determinant of that matrix works out to be 0, so we can fill in this box here. And this one is going to come from the determinant of 27, 167, 18, and 0. And we end up with this pattern where if you have a 0 on the bottom right, you end up just transferring down whatever's in the top right. So this is going to end up being 18. So again, this is a positive value. All of them now in our first column are positive. So therefore we're going to have an unstable system. Sorry, we're going to have a stable system. Okay, so I've just noted that down the bottom here, the system is stable. So we can proceed now with our steady state error calculations. So we've got 3 that we're going to consider, 3 different inputs I should say. And I'm going to use the error constant method to be able to work these out. So for steady state error with the error constant method, what we need to figure out is the system type. So the system type corresponds to, when you look at the bottom line of your open transfer function, this one here, we need to count the number of s's on their own, or integrators. So in this case, we can see that we have one s out the front of our system, which tells us that this is a type 1 system. Alright, so I've just given us now the table for steady state errors, and we're going to be able to solve for a couple of our errors just by using this table. So we've said that we have a type 1 system, so that corresponds to this row of our table. So we can say straight away that if we have a step input, that's going to mean that our error is equal to 0 for that system. And if we have a parabolic input, we can say straight up that our error is going to be infinite for that system. So the only one that we're going to need to go and calculate is if we have a ramp input, we need to evaluate what 1 on kV is. So if we jump back up to what we're asked to investigate, so we've got 3. This one here is going to represent a step input. Okay, remember a step is 1 on S, and we have a 2 on S in this case, so that means it's a step of a height of 2. This one here, it's going to be a ramp input, because it's on S squared, that represents a ramp. This one here is going to be a parabolic input, because it's on S cubed. Alright, so let's deal with the step one first. Alright, so when R is equal to 2 on S, that's a step. So looking at our table, system type 1 step input, that's going to mean that no matter what, we've got an error of 0, steady state error of 0 for that system. Let's now deal with the parabolic one, because that one's also pretty easy. So we said we had an input of 5 on S cubed, which was parabolic. So as a result, looking at this table, type 1 system, parabolic input, no matter what, this is going to be an infinite steady state error. So the only one that's a bit harder to deal with is when we have an input of 5 on S squared, because this represented a ramp with a gradient of 5. So to be able to work it out, we need to find this error constant, kV, and it's from the limit as S goes to 0 of S times G open. So we can substitute in our open transfer function. We have that from before. It was equal to this here, whatever was on the top line. So popping that in, okay, we can cancel S on top and bottom line. It's meant to be a plus. Substitute in the limit, so it's when S goes to 0, so we're going to get 6 times 3 over 9 times 18. And this works out to be 1 on 9. So we now need to convert this into our steady state error. And we can see from the table it's going to be equal to 1 on kV. The only catch is this table is based on having a unity input. So a 1 on S squared rather than a 5 on S squared. So all we need to do is multiply our error by 5, because it's going to be 5 times bigger than the unity one. Sub in, so we're going to get 1 on 9. And we end up with an error of 45 for this input. Alright, so that's the 3 answers that we were looking for. So if we wanted to, we could check this answer using MATLAB, and I've set up a code which is capable of doing that. Let's just scroll up to the top, sorry. So we've set up our transfer function and put in the overall or the closed loop transfer function here. I've also set up a time vector. This is just defining the time over which I want to see the response. So it's going to go from 0 to 100 seconds. Then what I've done is plotted first of all the step response. So that's what this line here is. It's giving me the step response to a time of 100 seconds. And this part here is just plotting the input, so I have both of them on the same graph, and I'll be able to compare them. So if we look at what it spits out, this is it. So the red line is the input, the blue line is the response. And we can see that with time, both of these curves get closer and closer and closer together until they're essentially the response is matching the input, which is what we wanted. So when they match, that means that we're going to have a steady state error of 0. And that's exactly what we found in our analysis just a moment ago. We said that for our step input, the steady state error was equal to 0. So if we now look at the ramp input, we found for that one that we had a error theoretically, of 45. That was this one here. So if we go have a look at what MATLAB thinks, if I scroll down a bit, it's this part here. And we look at the figure that we've got coming out. So again, the red line is the input, the blue line is going to be the response, and we can see that over time we start to approach this steady state where the difference between the input and the output looks fairly constant. So we can try and figure out what the difference in here is. Let's say I zoom in where we can see it's pretty constant, the difference. And we can try and calculate what it is approximately. So let me just shift this a bit. So we're looking at the difference. If this is about 400 at this point here, what we want to do is figure out what it is at the bottom here. It's probably easiest if I do this at 100 seconds because we'll be able to get exact numbers. So, so this is the input. At 100 seconds, our input is 500. And if we look at the end of our response curve, we can see that at 100 seconds, the response is at 455. So the difference between these two is 500 minus 455, which is equal to 45. And that's again what we calculated for the steady state error here for that response. So the last one that we have is the parabolic case, and we calculated theoretically that we have an infinite error. Again, if we simulate that in MATLAB, that's this section of the code here, and have a look at what happens. We can see that for this one, the difference between the input and the output curves is getting bigger and bigger and bigger with time. So as a result, that steady state error is just going to approach infinity as time goes to infinity. It's never going to reach 0, it's never going to reach a finite number, it just keeps getting bigger and bigger and bigger and bigger. So again, that agrees with our theoretical calculations. So that's all there is for this video, and see you in another one.